Hi everyone, welcome to Mostly Math. Today we'll be talking about some differential equations you might not see in a typical differential equations class. We're talking about differential equations of infinite order. What is the order? Well, it's the highest power of derivative that appears in the expression. For example, in this differential equation, harmonic oscillator, this is a second order differential equation, since y double prime is the highest derivative term that appears. These are the most common everywhere in physics, engineering, etc. This differential equation and a few others like it that we're going to talk about in this video have the ellipsis at the end, so basically it doesn't stop. There's a y triple prime, a y 4 prime, there's y to the 17th prime, etc. It just doesn't end. So we call the order infinite. And we're going to see if we can solve this bad boy today. Just a preview of what we're going to learn. We're going to learn that if the equation is linear, like we have here, we can actually solve it with an exponential ansatz. But it's important to check that it satisfies the differential equation, since these are pretty shaky conditions that we're applying here. There is a theory of the infinite order differential equations, but it's not as well studied as the finite order differential equations because some properties don't hold. Like, for example, it's not going to have a valid solution everywhere if you find it. So let's begin. All right, exponential ansatz, as you recall, is basically we're going to guess the solution. This is everyone's first line of attack. We're going to let y of t be equal to e to the st for some real variable t. And this tells us that we have y of t on this side, e to the st, is equal to, well, the first derivative just brings down a t. So let's remind you what this does. So y prime is just s e to the st, and y double prime is just s squared e to the st. And if we had y to the 17th, it would be s to the 17th, e to the st, of course, and it just continues on forever. So basically, by choosing the exponential ansatz, where we're going to replace differentiation with multiplication. So we have s plus s squared, and it continues on forever, multiplied by e to the st. And I have actually proven the formula that we need in another video, link in the description. We're going to need this geometric series type formula. X plus x squared plus x cubed plus etc. is going to be x over 1 minus x. In general, you can recall this if you wanted to leave off the first few terms. If you had x 17th plus x 18th plus x 19th plus etc. It will be nothing but x to 17th over 1 minus x. So it's the tail of the geometric series. You can always do this. Just FYI. Okay, we're going to use this. So this tells us that we're also going to cancel the e to the st's on both sides. Since e to the x is always greater than 0, we can always do this. So we have 1 is equal to s over 1 minus s, which we can solve pretty easily by multiplying both sides by 1 over s. This tells us that 2s minus 1 is equal to 0, right? So we have, just 1 minus s is equal to s. Then we add both sides. So we get 2s minus 1 is equal to 0. Or s is equal to 1/2, of course. So we've done it basically. We can now write our solution. So y of t is now some constant, e to the t over 2. And to find the constant, it'll be satisfied by looking at the initial value problem. We're given that 1 is supposed to be y of 0, which is a. So it tells us that a equals 1. So now our y is just e to the t over 2. It's pretty cool. Quite simple. I like it. And what I find interesting is that if we plug this into the solution, we do indeed get the result. So let's go ahead and do that. This tells us that y is equal to e to the t over 2. We've just solved it. Let's go ahead and plug this in. I'm going to need this formula again, so I'll just keep it here. Okay. All right, so if we plug it in, let's look at the right-hand side. I'm going to plug it in by looking at the right-hand side and showing that it's equal to the left-hand side. So we have s plus, no, sorry, we're done with s. S is now 1/2. So note that if we have y prime is equal to 1/2 e to the t over 2, and then y double prime is taking the constant down again, 1/4 e to the t over 2, and we continue on forever like this to be 1 over 2 to the n, e to the t over 2, yn is equal to that. So let's go ahead and plug that in. Can everyone see this? Pretty straightforward, just the exponential derivative multiplies the constant out front. Okay, so we have 1/2 plus 1/4 plus 1/8 plus etc. times e to the t over 2. And this series is nothing but this series here down below with s equal to 1/2. 1/2 over 1 minus 1/2 e to the t over 2. This is 1/2, so it's e to the t over 2. And it does indeed satisfy the property, which is pretty cool. Okay. Notice that it only worked because 1/2 was in the radius of convergence. You can easily find other infinite order differential equations that have the solution e to the 2t, for example, but then when you go and try to plug this into the series formula, it doesn't work since 2 is greater than 1, and we need the absolute value of x to be less than 1 for these geometric type series to work. In particular, I'll just show you an example that I got this for. So if you start off with this equation, 0 is 2 of y of t plus y prime plus y double prime plus etc. And if you try to use the exponential ansatz, you do find y is equal to e to the 2t, but when you go and plug it in, you get something that looks like this. Yeah, you get something that looks like, I didn't intend on doing this. Doesn't converge, so it doesn't work. Now you get something that has like powers of 2 plus 4 plus 6 plus 8 or something. 2, 4, 8, 16. And you have to sum it up. And this has to be equal to 0, or rather -2 under some conditions. So you'll be doing some sketchy stuff, and we're going to avoid doing sketchy stuff like that. Okay, let's go ahead and move on to the next scheduled example. We're going to consider a problem that I found on Facebook, actually. A problem that was interesting, and I didn't see the exponential ansatz solution there, so I decided to create a video detailing the solution. It's been a long time, so I'm not going to upload the video to the Facebook group. But if you want to try it out for yourself, go on the Facebook group. It's called Math Facts. This group has the tastiest integrals and series that I've ever seen. Basically, it involves a lot of Indian kids trying to challenge each other with the most difficult integrals and series that they can do. There's cool stuff there. Definitely check it out. And the problem that they gave us to do was the following. It's a bit more complicated. 4y of t is equal to minus y double prime. I'm using the y double prime is equal to y of 2 notation, you'll see why in a bit, plus y to the 4th derivative minus y to the 6th plus etc. We have an initial value problem of 2 variables now. Oh, incidentally, something I wanted to mention about the initial value problems. So we had a differential equation with infinite coefficients that can be completely specified by only one initial value problem. We had y of t is equal to e to the t over 2 for y of 0 equals 1 for the infinite order differential equation that we talked about. But shouldn't there be infinite initial value problems to specify the solution? I don't really know the answer to this myself. So if you do, feel free to leave a comment. All right, is the problem correct? Yep. It's correct. Let's go ahead. Start with this bad boy. Okay, exponential ansatz again tells us that 4 e to the st is equal to, okay, minus the second derivative. Well, no, sorry. Minus the second derivative, s squared plus s fourth minus s sixth plus etc. times e to the st. Now we need another series formula. So if we have this, we had x plus x squared plus x cubed, etc. is equal to x over 1 minus x. So if we let x go to minus x squared, we have on the right hand side, or left hand side, let's do the way. So minus x squared plus minus x squared squared plus minus x squared cubed, which is minus x squared plus x to the 4th minus x 6th plus etc., which is minus x squared over 1 plus x squared. Cool. Just going to note up here the result here. I'm going to multiply everything by a minus sign for convenience. X squared minus x 4th plus x 6th minus etc. is equal to x squared 1 plus x squared. That's the result that we need. Okay. So we're going to cancel the e to the st's again, just because we can. We have 4 is equal to, okay, let's sum it. We're going to sum it as follows. Minus s squared over 1 plus s squared. Now we have a polynomial equation which we can set equal to 0. 0 is equal to 4 times 1 plus s squared plus s squared. It is 5s squared plus 1. Oh no, but wait. We have a positive polynomial equal to 0. How can this be? We have something that looks like this. How can it possibly have roots? Well, they're complex, which is what we want. We'll see in a moment. See, no real roots. Still complex roots available though, which tells us that, I need more room. Okay, we have s is equal to square root 4. This is a 4, sorry. Square root of minus 4 over 5 plus or minus, which is plus or minus 2i over square roots of 5. This is a solution. We want this because if you've seen this sort of thing before, if you have an imaginary exponential ansatz, you'll eventually get sines and cosines. This is actually fine. Okay. We do need more room though. Plus or minus 2i squared to 5. Remember that. Remember that. Plus or minus 2i over square roots of 5. Plus or minus 2i over square roots of 5. Okay. S is plus or minus 2i over square roots of 5. So y is some constant a e to the plus 2i over square roots of 5. T plus some other constant b e to the minus 2I over square roots of 5t. And now we just have to plug in the initial value problems. Hopefully we get a sine or a cosine out. If we don't, that means we did something wrong. Okay. 0 is the first initial condition. We're setting this equal to y of 0 is equal to 0. We need this now. Sorry about that. Y of 0, which is, okay, a plus b, because these things are 0. Of course, e to the 0 is 0. Tells us that b is minus a, so our y at this point is equal to some constant e to the 2I over square roots of 5t minus e to the minus 2I over square roots of 5t. This is our solution at this point. We use the other condition to get rid of the other constant. 1 is being set equal to y prime of 0, which is, okay, we're going to keep the constant here. This term just takes the constant down, keeps the sign the same. But this term, these two signs cancel out, so it becomes a plus in the middle. This times, well, we can factor out the constant. 2I over square roots of 5a, it becomes 2I over square roots of 5t plus, like I just said, e to the minus 2I over square roots of 5t. Evaluate this bad boy at t equals 0, which is 2IA over square roots of 5. 1 plus 1 is 2 times 2. It's messy. Just bear with me. Okay, so this tells us that a is equal to square roots of 5 over 2 times 1 over 2i. You'll see why I did this in just a moment. This tells us that y of t is now equal to square roots of 5 over 2, 1 over 2i. We have our cool crap, 2i over square root of 5t, excuse me, minus e to the minus 2i over square roots of 5t, which we should hopefully recognize this as the sine of this crap here. So y of t, square roots of 5 over 2 sine 2 over square roots of 5t. This is the answer. This problem was a bit more involved than the last one, but it's really just simple algebra after we let the exponential ansatz again. Note again, we only needed 2 initial conditions to solve this infinite differential equation, which is pretty strange in my opinion. 5 over square roots of 2, yep, excellent. Okay, let's go ahead and note what we learned here. Y of t is, I'll write it down in a bit. Just bear with me. So we are actually going to plug this into the differential equation that we have above and see that it solves it. It's important for us to do this in this context because we don't really have a mathematical understanding of what we're dealing with. So we got to plug it in every time because I can't guarantee that these things exist, and if I don't plug it in, I get things that converge, like adding up all the integers, and we just don't really want to do that. I mean, maybe you can. I don't know. I don't really understand this, so I'm not going to do things that I know I shouldn't understand. Okay, for the purposes of checking it, y of t we know to be square roots of 5 over 2 sine 2 over square roots of 5t, which we're going to call this frequency omega, 1 over omega sine omega t. Just for record-keeping purposes. All right, let's plug this bad boy in. As before, we're going to start from the right-hand side and ensure that it is the same as the left-hand side. Let's get started. Okay. right-hand side of this expression is equal to negative. Oh, well, first we have to, yeah, that's good, that's good. Okay, there's going to be a common factor of 1 over omega everywhere. And this is the second derivative. It's actually minus the second derivative. Okay, first, okay, so each derivative brings in a power of omega. Minus the second derivative, each derivative brings in a power of omega. So this brought down 2 powers of omega, and first derivative, sine goes to cosine. Second derivative, cosine goes to minus sine. Okay, great. Next term, we're going to get 4 omegas now, and we have to differentiate this twice. This thing, including the minus sign. So sine goes to cosine, and cosine goes to minus sine. These two minus signs cancel out, so it's positive. One last one we're going to do. We're going to put 2 more omegas, and we're going to take 2 more derivatives. Sine goes to cosine. Cosine goes to minus sine. And this, of course, goes on forever. Keep the W omega factored out. We're going to actually factor out the sine omega t as well. So we have omega squared plus omega fourth plus omega sixth plus etc. You probably can see that we need a series at this point. It's not going to be exactly the one that we solved it, but that's okay. We're just going to change this plus to that minus to a plus, and that plus to minus. I did this by letting x go to minus x squared. Whatever, you can do it. I trust that you can do it. I know this is true. Too many series is going on here. Okay. So it becomes 1 over omega sine omega t, and then we have omega squared over 1 minus omega squared. And I'm just going to write as a quick note here. Note that omega squared over 1 minus omega squared is plugging in what omega is now, this thing, 2 over square root of 5 squared, 1 minus 2 over square root of 5 squared, which is 4/5, over 1 minus 4/5, which is 4/5, over, okay, 5/5 minus 4/5 is 1/5, and the fifths cancel, equals 4. Congratulations. This is nothing but 4 1 over omega sine omega t, which is 4y of t. We're done, which is the left-hand side. Excellent. Congrats. If you follow me this far, I'm sure you can come up with your own wacky examples of this sort of thing. Feel free. Leave some comments so I know that you're live. Let's go ahead and do one more quick example. A bit more involved. Well, less involved in the computational aspect, more involved in the sense of, say, overall importance, whatever that means to you. Okay, let's get all of this gone. Okay, people. Ready for it? Okay. Let's do it. All right, gamma functions. Who likes gamma functions? I do. I like gamma functions. Okay. We know this identity is true. We have x times gamma of x is going to be gamma of x plus 1. Very important. It's a generalization of the factorial, of course. N factorial is equal to n minus 1 factorial. I don't need to bore you with the details about the properties of the gamma functions. Now, what is interesting is Taylor series. Taylor series expansions. If we have a function x plus a, we can Taylor series expand it around the variable a itself to be approximately f of x plus the constant times the derivative plus 1 over 2 factorial constant squared second derivative. This continues on forever. You may see where we're going with this. We're going to actually expand the gamma function around x equals x, plugging in a equals 1 to this expression here. All right, this becomes gamma of x plus d gamma by dx plus 1 over 2 factorial d squared gamma by dx squared plus, notice it goes on forever. You can see where we're going here. Now I'm going to subtract this from this and let it be equal to 0. 0 is equal to 1 minus x, gamma of x plus d gamma by dx plus 1 over 2 factorial d squared gamma by dx squared plus, etc. So now we have an infinite order differential equation for the gamma function. You may have heard that the gamma function doesn't satisfy any differential equation. Well, this is true for useful differential equations, in particular second order, homogeneous, whatever, the equations that constantly appear in physics. But the theorem which forbids this, Holder's theorem, doesn't have anything to say about the infinite degree differential equations, which are useless. This formula is useless as far as I know. And moreover, it's an example of what I was talking about earlier. It's not valid everywhere in its domain. So let's draw a quick graph of the gamma function. This is probably going to be wrong. I don't care. Okay. For positive, and it looks pretty normal, just like increasing, whatever. And at the poles, which are all the negative integers, has nasty infinite behavior. And it goes down too. It goes down too. Okay, nasty infinite behavior. Goes up forever, and then comes down like this or something. And then up, up, down. Up, down, whatever, who cares? It's not important. I'm not trying to draw you the best ever graph of the gamma function. What I am trying to tell you though, is if you look at a pole, and then you draw a circle around it, some radius, there is a theorem about this particular differential equation that says it's only valid for regions outside circles of some fixed radius around the poles, which is very unusual behavior for any second order or finite order differential equation. This means that the solution is not smooth in some sense, since it's not valid everywhere if you find it. So from a mathematical perspective, it's less useful because it's not valid everywhere. In particular, this equation is valid everywhere, so it is a defining property of the gamma function. But satisfying this differential equation is not, because it's not valid everywhere. Okay, people. That's about all I have to say about these infinite order differential equations today. If you have more, I'll be glad to see them. Please leave a comment, like, subscribe. See you next time.